In this video, we're going to cover how to estimate linear regression models using R. We're not going to cover the mathematics underlying linear regression or how to interpret the results. Those topics will be covered in other videos. Here, we're just going to focus on estimating the models themselves. So to get started, after setting our working directory and clearing out our R environment, we can load the data we want to use for analysis. In this case, we're going to be using data from a paper on subnational policy authority and educational attainment. The data we've loaded is named analysis data. Let's take a look at the names of the variables so that we know what they're called when we want to use them in our linear regression models. We can see here that in addition to the country, Gleditch Ward code, and year variables used to identify observations, there are several variables related to educational attainment, FEM-attain and all-attain, some variables related to subnational policy authority, and then a bunch of control variables that we can potentially use. So let's start with a simple linear regression. Say we want to answer the question, how does subnational fiscal autonomy, that is the authority of subnational units such as states or provinces to impose their own taxes, relate to educational attainment? In this case, let's look specifically at educational attainment in terms of secondary school completion rates among girls aged 15 to 19. So the most basic function that we use for linear regression is the LM function. In this case, we're going to use FEM-attain as the response or dependent variable and subtax as the predictor or independent variable. The basic syntax for linear regression in R is LM, then we provide the formula in the format Y, the dependent variable, then tilde, and then X, the independent variable. We then specify the data that we want the model to use. So in this case, we'd use the LM function. We'd specify the dependent variable FEM-attain, then the tilde, then the independent variable subtax, and the data we want to use is called analysis data. So let's run this model. We can see here that when we run the model, we get a little bit of output printed to the console. We get information on the formula and model call, and we get the coefficients for the intercept and the independent variable. If we want to access and use more information about this model, we have to save the model as an object. So let's name it model 1. We use the assignment operator and otherwise use the same syntax that we were just using. If we just call model 1, we get back the exact same output that we just got in the console. This contains the coefficients, obviously, but if we want to use this for something such as making a regression table or even just interpreting our results to see if any of these coefficient estimates are statistically significant, we want more detailed information. We want the standard errors, the p-values, etc. In this case, we can use the summary function to get this information. So if we call summary of model 1, you can see that we get a bit more information printed out in the console. We get the function call as we did before, the residuals, information about the distribution of the residuals. In addition to the coefficients, we also get a standard error for each coefficient estimate, the t-value, the p-value, and some stars indicating whether or not that variable is statistically significant. Here we can see that our predictor variable subtax has a statistically significant effect on our dependent variable, and we can see that the estimate for the intercept is statistically significant as well. So in addition to just the information that's printed out by the summary function, there's also a lot of other information stored in the model fit object that we saved. Let's take a look at that object real quick using the names function. So we can see that there's components called coefficients, residuals, effects. We have an object containing the fitted values, information on the function call, information on the model. This is a list, so all of these components of the list can be accessed using the $ operator. So let's look at a couple other ways to access the coefficients besides just printing out the model output or calling summary. We can use the $ operator, so model1 $coefficients. This prints out the coefficients, or we can use the coef function, which gets us the same output. So far we've looked at a simple linear regression of one dependent variable on one independent variable, but frequently we actually want to use multiple linear regressions. So we want to include control variables in addition to our most important predictor variable. For multiple linear regression, we can still use the same LM function. We just add the additional independent variables. The basic syntax is almost the same. LM, then Y, the dependent variable, the tilde, and then the independent variables, X1, X2, and X3. We put a plus sign in between each of the independent variables to include them in the model, and then we again specify the data that we want to use for this analysis. So let's take a look at the relationship between educational attainment and subnational tax authority again, but this time let's control for whether or not the country in question is a democracy and how wealthy the country is. So here we're going to save this object as model 2. We have our same dependent variable, our subnational tax authority independent variable, and then we add on the natural log of GDP and a binary indicator of democracy. Now, if we take a look at the results of this model using summary, we can now see that we have coefficient estimates for GDP and democracy as well, and also, of course, standard errors and p-values for these estimates. And we can see that these control variables have a statistically significant effect on the outcome as well, but that the effect of our independent variable, subnational taxation, is still statistically significant. So far, we've focused on linear regression, which is also known as ordinary least squares, or OLS. This is only one way of estimating a regression model. In various cases, you might want to use different types of regression models, or you might encounter different types of regression models in papers you're looking at or projects you're working with. So for instance, if we have a binary dependent variable, so say that we were using this indicator of democracy not as an independent variable, but as a dependent variable, we might want to use a logistic regression due to some of the nice statistical properties it has for dealing with binary dependent variables. The syntax is very similar to that for linear regression, but instead of using the LM function, we use the GLM function. So here we have model 3, GLM instead of LM. This time we have democracy as our dependent variable. And let's just use GDP to see how the wealth of a country is related to the likelihood of it being a democracy. So we have GDP as an independent variable. We're still specifying the data frame we want to use, but we also have to add an additional argument for the GLM function. We have to tell it what type of model to use. In this case, for logistic regression, we say family equals binomial and the link function equals logit. So if we run this code, and then we take a look at the output using the summary function, we can see that we get output that's very similarly structured: information on the function call, information on the residuals, information on the coefficients, and some goodness of fit statistics. And you may notice that GDP is a statistically significant predictor of democracy. So GLM, the function we're using, stands for generalized linear model. This is why we have to give it this piece of code that tells it which type of model to use. In this case, the type is the family of the model. As the term generalized suggests, ordinary least squares linear regression is a specific type of GLM, so we could also estimate that model using this function. Usually we don't, because the syntax for the LM model is a little simpler. We don't have to give it family argument. But if you want to know how to estimate a linear regression using GLM, it's the same code we would previously have used, but we add the family argument. In this case, family equals Gaussian, which refers to the normal distribution, which is what underlies ordinary least squares regression. So if we run this model 4 and we look at a summary, we can see that the output is identical to what we see with the LM function. And that's because this is essentially running the same model. So right now, don't worry too much about the statistical details of the different models. That's not really the focus here. The main takeaway is that these different regression models produce very similarly structured output. Thus, we can use the output in very similar ways. So packages such as Stargazer or TextReg, which create publication grade replication tables, can work with the output from most commonly used regression models. Similarly, your code is going to look very similar for generating, say, coefficient plots or other types of visualizations from regression models, regardless of what the underlying statistical model for the regression is. That's all for this video. In the next video, we're going to cover how to make these publication grade regression tables.